Uh, this is the outline of my presentation. So first we'll discuss what is energy, what are the different forms of energy, and then renewable energy. We'll discuss what is renewable and what is the difference of it from non-renewable energy sources. And then energy storage system, solar cell basically, there are other energy storage system also, but we'll discuss in details about solar cell only. And then we'll give conclusion and reference. So what is energy? See, when we speak of energy, it is often connected to spirituality. People always tells us keep yourself with surround yourself with positive energy, all these things. But in science, energy is the ability to do work. Now what is work? In physics is a force displaces an object, then the work is said to be done. If you're supplying force, if you're providing force and nothing is moving, there is no motion, then uh, it is said that there is no work done. Now, this is the definition of energy. You all know, we have studied this in class 9 or 10 maybe. So as I already mentioned, I am not going to speak anything which you don't know. It is just kind of revision, okay? So now we know that there is a law of conservation of energy, and that is energy can neither be created nor destroyed. Very popular, fine. Now if energy can neither be created nor destroyed, now tell me why media keeps telling us that we are running out of energy. That is, we have to save energy, we should be energy efficient, like all this. Now, is this media making fool of us? No. Even if energy can neither be created nor destroyed, but they gets converted from one form to another form. Suppose say one form is useful for us, but when we use energy, suppose for whatever applications we want, now it gets transformed to some other form, which is not useful anymore. Like they generally gets converted to low grade inconvertible heat. So that means that's how we are losing energy. There, energy is there. Energy can neither be created nor destroyed. It's already there, but the form, it's converted to some other form which is not useful anymore. So that's how we need to be energy efficient. We need to learn how to store energy. So these are the different forms of energy. You can find many other forms available. I have mentioned just few of here, and here the symbol where you can see this green recycle symbol is there. Though those are renewable sources of energy: geothermal, tidal, biomass, solar energy, wind energy. So all this. And in I think all of you remember in class when we studied mechanical energy can be divided into potential and kinetic. Potential energy is due to its position of the object, and kinetic energy is due to motion of the object. Now, potential energy gets converted to kinetic energy when the object moves. Suppose some object is at greater height as compared to the other. Now, how do you know that? Suppose two boxes are there, one at upper table, one at ground floor. Now, generally we make mistakes that they are at equal energy. We have this shortcomings of grasping potential energy because it is placed at higher height at table. Suppose you remove the table, then it will fall down because of gravity. That potential is due to gravity. It has energy, it is moving down. Now moving down with kinetic energy, so potential energy gets converted to kinetic energy. Now these are the different forms of energy. Now we'll move on to how much do we consume. As I already mentioned in the first slide, maybe we need to store energy, maybe we need to be energy efficient. All the time media is telling us that uh, um, we are going nuts how to save energy, all these things. Now how much do we consume? So as you can see, this has been taken from IEA reports. Here we can see that our consumption of energy has increased over the years. Like see, till 2019 we have the data. So how use of traditional biomass, it has been almost similar all throughout the year, not much increment. But for coal and oil and gas, nuclear gas is also increasing after, I think it's after 2010 or something. So here we can see coal and oil, these two sources of energy are used very much. We consume it too much. Now, what is the quantification of this energy uses? You can see 16,000 terawatt hour. Now, 16,000 terawatt hour. What is 1 terawatt hour in joules? We know that SI unit of energy is joule. It is 3.6 into 10 to the power 15. So you can imagine how much energy we are using. Now, here it is other renewable sources, non-renewable sources it is mentioned. Now, in next slide, we'll move on to what is renewable and what is non-renewable. Why we can't keep using non-renewable sources? Why we need to move to renewable sources? Now, renewable energy, this is a good idea. Why? Because it can naturally replenish themselves. Now, naturally replenish themselves, example is solar, wind, water, all these things. But non-renewable coal and oil, which we use too much in the last few decades, they are non-renewable. That means if you use it once, they change their form to some other state and it cannot be used anymore. So if we are done using all the coal and oil and fossils available to us, then what will you do? How will we survive? How this world will move? Obviously it will move round and round around sun, but will we be able to have the lifestyle we are having now? So that's how the idea, a good idea of renewable energy came into the picture. But there are some shortcomings regarding this renewable energy, because non-renewable energy source can provide you as much as power you want on your demand. You want more power, you'll get. But renewable sources has some shortcomings, because like solar, wind, all these things, when you say solar, wind, these are hydro, these are the examples of renewable energy sources which replenish themselves: hydro, solar, wind, bioenergy. So this is what happens, they are not available all the time. So hydro, we need force of water. Solar, we need light there. So it is not like we solar panel if you use every day, it doesn't sunshine, isn't it? So it's like not feasible for this high amount of energy consumption, these renewable sources. Now, if renewable sources are not feasible enough uh, to replace non-renewable source, we totally want to replace non-renewable source with renewable source of energy. Now, to replace that, we should have that capacity. We should have the capacity to generate as much power on the demand of day-to-day life. Now, how to accomplish that? We can store energy. Now, renewable energy is a good idea. Now, storing energy is a better idea. So we'll move on to storage of energy. Now, energy storage system. Actually, maybe I'm going fast. I cannot see expressions of student. If I was in an offline class, I would have asked like, do you understand this part or not? I could have understood from their expression as well. But anyhow, uh, shouldn't complain anymore. So energy storage system, as you can see, there are different energy storage system. Batteries, we all know, very popular. But lithium ion batteries, those are used in our phone, laptop, all the things. So then solar cell, mechanical storage is also there, which harnesses kinetic or gravitational energy. Then it uses hydrogen, pumped hydropower. So some of the images are also shown here: hydropower, wind power, solar panels, batteries, large lithium-ion batteries. So all of these are the available energy storage system. Now we'll be basically talking about solar cell. See, as I already mentioned that I am also amateur in the field, I prefer learning from the basics. Now solar cell is quite popular, but still we are um, we have to develop it so much so that it can replace non-renewable sources, so that it can help us to so that it can help us to replace non-renewable sources. I already mentioned that. Now moving on to what is solar cell. So this is like I mentioned in the first slide that there will be no complexity because we just had lunch. But then at least once basic in details I should present here, because I should warn you about the complexity. It's not like solar cell will be given to your hand, you will use it. Since you're a student of science, If you aspire to become scientist, you should learn how to love the basics and also the tough part of science, not only popular part. So here the solar cell is a large PN junction diode. So about PN junction diode, I think you studied in class 12. That is question number 1. Still we want to recap it. Now, which works in photovoltaic mode. Now, what is photovoltaic mode? That is question number 2. And it converts light energy into electrical energy. So how does it convert? That is our question number 3. So, okay, PN junction diode, P and N are semiconductor material. What is semiconductor? What is P? What is N? So, all these details I'll be discussing with you. Now, this is the physics of solar cell. So, we're moving on to physics of solar cell. Here, in the first diagram, you can see that energy band diagram. Energy band diagram, when I say every time I went for a class, in any period, first class, when I ask students, we have studied Bohr's atomic orbital theory. Please imagine Bohr's atomic orbital theory picture. You have a nucleus at the center, and electron revolves around that nucleus in a circular orbit. So that orbit has a sharp path, one single orbit. Now we're speaking about an crystal, but then in band, not in orbits. How bands are formed? So I would have expected answer from students. I don't know, maybe all of you know this, but still I'll repeat as from my experience. I know many of the students, when asked in Bohr's orbital theory, in atomic theory, there we studied just one orbit there. How come we have band? So suppose see carbon. What is the atomic number of carbon? 6. Now that configuration is 1s2, 2s2, 2p2. But in p orbital, we can have how many electrons? In s2, p, we can have 4. So only 2 electrons are occupying, other 2 are empty. Now D also available, but we don't have enough electrons for carbon atoms. I'm giving you the example of carbon atoms so that we can understand first why we have band. Then we'll move to energy band diagram. Now, when you have a crystal of carbon, not atom of carbon, crystal of carbon, suppose say diamond. Diamond is a crystal of carbon. Graphite, lead, carbon nanotube, all these are crystals of carbon, allotropes of carbon. Now, when carbon atoms combine together, there are so many 1s2 level. What is the configuration? 1s2, 2s2, 2p2. Now you have so many carbon atoms. That means you have so many 1s2, 2s2, 2p2 like that. So 1s2, 2s2 are totally filled, 2p2, half of them are filled, half empty. So that's how this 1s2, 1s2 level, when they, uh, uh, how to say, when they bond together, when one carbon atom forms bond with nearby carbon atom, there forms an interaction between these levels also. And that's how you get a bend. Now you don't have only one single 1s2 orbitals. You have many 1s2 orbitals which are interacting with each other. That's why you get band. Now what is valence band and what is conduction band? Now valence band means where the electrons in the crystals are bonded in a, maybe in covalent bond, say bonded in suppose in diamond, their carbon forms a covalent bond. So carbons forming covalent bond, so all those bonded electrons in a covalent structure will be there in valence band. Now who forms the conduction band? That means 1s2, 2s2, 2p2, another 2p2, they will form covalent bond, so all those will be there in valence band. Now conduction band is somewhere where this empty states of p level will combine together and will give you conduction band. So conduction band means empty states, available states of electron where you can have electron but there is no electron. So possibility of having electron is fine in conduction band, but in valence band you have all the electrons. In conduction band there is no electrons at absolute zero temperature. Why I'm saying absolute zero temperature? Because temperature plays a major influence on the movement of electron. Temperature provides energy, thermal energy of fluctuation. So when electrons who are in a covalent bond structure in valence band, they vibrate, they will get energy and they can pass to the conduction band. Conduction band, which is at higher energy state. Why at higher energy state? Because as you know, 1s2 low energy, 2s2 higher energy, 2p2 far higher energy. So you are going further and further from the nucleus. Those are highly energetic. So that means, so those 1s2 interaction will give you valence band of lower energy, while empty states will give you conduction band of higher energy. So electrons, if they want to move, or if you want electrons to move from valence band to conduction band, you have to supply them enough amount of energy to move them from valence to conduction band. So now are we clear with why we have valence band and conduction band? So I'm assuming that we are clear with that. So now we'll see how this difference in valence band and conduction band, that is called energy gap, how is different for different type of material. Different type of material in the sense we'll divide it in terms of insulator, semiconductor, and conductor. Conductor is what? They conduct electricity. Now, what do you understand by conducting electricity? That means where electrons or charge can flow. Basically, electricity is nothing but flow of charge. When charge flows, we have current. So in here, valence band and conduction band in conductor, they are overlapped with each other. So these electrons in valence band can easily move to conduction band. Okay, example is copper, aluminum. These are examples of conductor. Now, semiconductor, you can see band gap, that is how much energy you need to move from valence to conduction band, in between that of insulator and conductor. In conductor, there is huge gap between valence band and conduction band, so that these electrons cannot move to conduction band. Okay, so in semiconductor, if the temperature is not 0 Kelvin, if it's a room temperature, then the covalent bond structure in the valence band breaks and some of the electron moves to the conduction band. So when electron moves, then you have current in the circuit. So here the conductivity of semiconductor is in between that of conductor and insulator. In insulator, electrons cannot move from valence to conduction band because the energy gap is too high, and in valence band they easily move because there is no gap. And in semiconductor, they can move, but you need to provide some kind of energy, maybe thermal, maybe optical. Okay, so this is the how to say significance of semiconductor. Now, if it was a class of just semiconductor physics, I would have asked, if already we have conductor where electrons can move easily, why we use semiconductor? Because we need to provide energy. Why do we need to provide energy? If someone is moving freely and is giving us current, why do we need to use semiconductor where we need to provide energy? We are trying to become energy efficient, so we should get some output of in current without supplying any kind of energy. Then that one only we should prefer, isn't it? Should we prefer only conductor and we should altogether avoid semiconductor? Because in semiconductor we need some kind of energy, we should provide some kind of energy for the conduction to take place, for electrons to move. But in conductor, we don't need to provide that external amount of energy. Is that so? No, actually what happens, semiconductor is very efficient because we have proper control over its valence band, conduction band structure, band gap. We can use any amount of energy we want. We can tune its conductivity, we can tune its band gap. So that's how in device application semiconductors are generally used, but conductors are used where we need to pass current, one from higher potential to lower potential. You want to move electrons, then you use conductor, just simple as that. But to prepare device, semiconductor is the best option. That's why we need to study semiconductors. So I am diverging away from my topic, where actually we are discussing solar cells, but we're going more depth into semiconductor. Anyhow, so semiconductor, one example is silicon crystal. So silicon has atomic number 32. Please correct it if I'm wrong. I often get confused with silicon and germanium. Silicon crystal and germanium, both of them are actually semiconductor. Now, silicon and germanium, both of them has valency 4. That means on outermost electron, outermost shell, or outermost orbital, they have 4 electron. Now, if valency is 4, but according to octet rule, for an atom to become stable, we need 8 electron. Now, what this silicon atom will do? They will share their electrons with each other, with nearby silicon atom, and form covalent bond and will become stable by having 8. Suppose that this silicon atom has 4 own electron. They have 4 own electron in the valence orbit. That is, the 4 is their valency. Now it needs 4 other silicon atoms to become stable. So they share and they create this covalent bond structure, and that's how we have this silicon crystal. Now that's why we have valence band and conduction band. See, we don't have only one silicon atom, we have many silicon atoms. So we have valence band and conduction band. Now when we don't apply any kind of energy here, we are not providing any thermal energy, we are not providing optical energy, so this bond remains intact. So when this bond remains intact, electron does not move around. If electron does not move around, then there is no conductivity. So at 0 Kelvin, at absolute 0 temperature, there is no conduction, there is no flow of electron in semiconductor. So this kind of semiconductor is called intrinsic, where we don't have any kind of impurity. But there is other type of semiconductor that is called extrinsic semiconductor. Now extrinsic semiconductor can be of two types, N and P. N is when we induce some kind of impurity which have 5 valence electron. For silicon atom, as we already mentioned, they have 4 valence electron. Now they need 4 more electron, but you are supplying how much? 5. So one will be in excess. So you are not just giving one this PV, that is so, and in here B, that means, oh sorry, so here B means, here it is 4, it is 3. So boron, it has 3 valence electron, but then silicon needs how many? 4 valence electrons. So there is one empty space. So this empty space is called holes, and this obviously excess electron is called electrons only. So this lead is actually providing you excess of electron, and this B is providing you excess of holes. So now we'll discuss what is electrons and what is electron, how electron acts as carrier in semiconductor, and how holes acts as carrier in semiconductor. Now moving on to first here holes. Okay, so charge carriers in semiconductor. So we know how many type of semiconductors are there: intrinsic and extrinsic. Intrinsic, no impurity. Extrinsic, we have provided some kind of impurity there. In one case with 5 valence electron, in one case with 3 valence electron. When we provide 5 valence electron, but we only need 4 valence electron, then we have one excess. So one excess means there will be excess of electrons. Electron is negative, so we call it N type. And when we provide 3 valence electron, but we need 4, so that means we have one vacancy. So that is, vacancy means vacancy of electrons. So instead of negative, there is an empty space, so that one we call it positive, P, holes. So N type and P type. So electrons in conduction band and holes in valence band are our charge carrier. Now mind it, why only electrons in conduction band are charge carrier? Because electrons in valence band are already in a covalent bond structure. They are in covalent bond structure, they are fine, they're not moving from here and there. So if they are not moving, are they charge carrier? Will they give us current? Will they give us conductivity? No. They have to move to the conduction band. What was conduction band? Empty states, available states where electron could be there, but there was no electrons. Now this excess electrons, because of giving pentavalent impurity, that is 5 valence electron, this excess electrons will move to this conduction band where we have available states for electrons. Now there are enough number of empty states, so electrons will keep moving from here and there. So these electrons in conduction band are charge carrier, but not electrons in valence band. Electrons in valence band are never charge carrier, because why? They are bounded to a covalent bond structure. But who can be charge carrier in valence band? Holes. Because if you provide some kind of energy, maybe thermal energy, then electrons will move from valence to conduction band and they will leave behind empty space. This empty space is called your holes. Now some student gets confused why we don't have holes in conduction band. Because in conduction band we don't have covalent bond. We have covalent bond in valence band. So electron has to move out from a covalent bond, then only you will have a holes. Holes means nothing but from a covalent bond structure, if an electron moves out, that empty space is holes. Not every empty state, not every available state for electron is your hole. So there are enough number of empty states available and electron states in conduction band, but those are not holes. They are just states where electrons can move from one place to other. But in valence band, electrons were occupying some specific positions in covalent bond structure. From when they move out from those specific positions, then those are called holes. So electrons in conduction band, excess electrons in conduction band where they can move around, those are the carriers. And holes in valence band are called charge carriers in semiconductor. So in metals, we have only one kind of charge carrier, that is electrons. But in conduction band, we can have two kind of charge carrier. One is electron, other is holes. So we already said how electron moves in conduction band. That is fine. Electron, because we have enough number of empty states, electron moves around in conduction band. Fine. Now how holes move? Holes move with, suppose, how do I say? Now I'm working in Bharat Institute. Suppose I got some better opportunity in how do I say, maybe I got a job in Nagaland University, there is some vacancy, so I moved from Bharat to Nagaland University, because that is central obviously. So so if I move to Nagaland University, then there will be vacancy in Bharat. So directly that vacancy didn't move to Bharat. From Nagaland University to Bharat, the vacancy didn't move. What I did, an electron, that is a faculty, moved from Bharat to Nagaland, then only there comes a vacancy in Bharat. So that means one electron will move in valence band, then only there will be motion of holes also. That is, if electron moves from left to right, holes move from right to left. If I move from Bharat to Nagaland, vacancy move from Nagaland to Bharat. So I think I'm clear with that. So now next, we are done with p type, we are done with n type. Okay, energy band diagram. Why we have energy band diagram? Who are charge carriers in p type and n type semiconductors? Done. Now what we do? We make diode of p type and n type. Diode means we have two sides. Okay, one is p, one is n. We bring them together and make a contact point. So that yellow region you can see here, this line is your contact point between p type material and n type material. P is empty holes, n is excess of free electrons. What we did here, in intrinsic semiconductor, we put impurities with 5 valence electron, but we need only 4, so 1 electron will be excess. So there will be so many electrons in excess. But in p type, we have put 3 atomic number, 3 valence electron atoms in intrinsic semiconductor. So we have empty states here. So those empty states are giving you holes. Now when you connect them together, what will happen? Because of diffusion, these electrons, there are so many electrons here, they will repel each other. By Coulomb's law, we know that like charge repel each other. Here also like charge will repel each other. So they will move from one side to other. So these electrons will move here, these holes will move here. Now, so what happens? They wanted to give up an electron, they gave up. They wanted to receive an electron, they received. Now they become stable. So when someone gives off an electron, they become positive. So these are your positive space charge ion near n-type material. In n-type material, we have excess of electrons. So they want to give up this excess of electron because of this repulsion within themselves. So they gave up to the p side. Now p side wanted to receive an electron, they received. Now they become stable. So whatever they wanted to give up and wanted to receive, everything accomplished. They are done. They become stable. So here, because they gave up electron, they become positive. Because they received electron, sorry, in p type they received electron, so they become negative. But they are stable now. Now what happens? They does not allow further movement of these free electrons or holes. Now see, these are positive. Here we have negative in p side. Now these electrons, even if there is repulsion in between them, they cannot move to this side. Initially they can, when you just first made the contact. Now they cannot. Why? Because you have negative space charge here. Again, this negative space charge will repel this electron from moving on to this p side, because at the boundary you have negative space charge ion. At the boundary of p type you have negative space charge ion. That's why these free electrons cannot move to this side anymore. And similarly, these holes also cannot move to this n side. So this region where we have stable space charge ion, they're stable, they don't want anything now, they don't want to move now. So this is called depletion region. Now we know an electric field is created from the direction of positive to negative. So here we have an electric field that is called potential barrier. Now potential barrier opposes the flow of this charge carrier. So junction diode basics I taught now. So there is so much more into this, but whatever is important for solar cell, only that part I'll touch. Now we have, these empty holes cannot move, these free electrons cannot move because of this space charge ion. Why we have this space charge ion? Because they have become stable now. They received what they want, they gave up what they want. So they are stable at the barrier. So that's why this is called barrier protection. Now this is the example of a solar cell. Here what we are doing, we are providing light, we are providing thermal energy. Light is a source of energy, isn't it? HDU, photon. Light is nothing but photon. I think that one also studied. If I want to take a lecture, that will be another lecture altogether. So I won't go there. Just consider light as a source of energy. Now that when you provide light here in the depletion region, they are stable now. Still then, those electrons in valence band, if you remember this, suppose they are stable now. Again, consider this only. These electrons in valence band will take the energy from light and move to the conduction band. So there will be creation of electron and hole pair. Holes in valence band, electrons in conduction band. So this, because of light, there will be electron and hole pair generated. That is, electron will move from valence to conduction band. So when this electron hole pair is generated in the junction, they cannot recombine. They cannot come back to anywhere else. Okay, but here, if suppose in this space in p type where we have excess of holes, we created some kind of electron and hole pair by providing light. Now what happens? One hole created, one electron created, but this electron will have many empty holes to fall back. So the possibility of recombination is too much here. Again, in this region, if you create electron and hole pair, one electron and one hole, because of light, we already have free electron, but because of light we created one electron, one hole. Now that hole can get recombined by so many electrons here. So the recombination possibility in this regions is too much high. So we don't want to waste the electron and hole pair produced by light. So we'll produce that only in this junction, because in this junction we don't have excess of electrons for holes to recombine. We don't have excess of holes to electrons generated to recombine. So we produce electron hole pair in the depletion region. Now when electron hole pair is produced in the depletion region, what happens? Because of this electric field, there is electric field, isn't it? Nearby n type material you have positive, nearby p type material you have negative. So this again is shown here. P type, at the barrier of p type, at the edge of p type you have negative space charge ion. At the edge of n type you have positive space charge ion. Now when their electron and hole pair is created here in the junction, in the depletion region, these electrons will move to n side. Why? Because you have positive here. At the edge, you have positive. So whatever electrons created in the depletion region, in this junction, in this white area, suppose this is your depletion region, here due to light, electron and hole pair are produced. So because this is positive, even if it is n, this is n type only where we have excess of electrons, but at the edge we have positives. So these electrons will move to n, and these holes will move to p. So that way, if you continuously provide light, more and more electron and hole pair will get generated, and electrons will move to n side, holes will move to p side, and they will get accumulated here. Suppose that this connection, this external connection, remove it. So if you remove this external connection, what happens? At this lower edge of p type, there will be so many holes. See, positive sign towards this side, positive sign towards this side. That means whatever electron hole pair produced here, because of this negatives, this negative layer at the junction in p type, this holes will move towards this, and electrons will move towards this, because we have a positive layer at the initial initial edge there is positive. That's why electrons will move here. Now electrons accumulating in this n, holes accumulating in this p, there will be large, very huge potential difference between these two. That potential difference will give us voltage. Now here potential difference is nothing but voltage. We know the definition of voltage is what? Potential difference between two points. That is your voltage. Now here we have shown, here I have shown you the IV characteristics of solar cell. Now here we can see this is VOC, this is ISC. VOC, what is VOC and what is ISC? I'll take just 5 more minutes, maybe I'm taking more time. So here see, VOC is open circuit and short circuit. Many a times we get confused, even though we know, we tend to get confused. Short circuit means when resistance is very low, when there is zero resistance, that is your short circuit. Zero resistance means there is no constraint to the flow of electrons. Electrons can move very fast through the circuit. Then that is zero resistance. Now open circuit means when the resistance is infinite. Now suppose at these 2 points I have charge. I am not connecting any kind of wire. So will electrons move from this to this? No, because there is no path. There must be some path for electrons to move. If you don't connect anything, via what electron will travel? So that is R equal to infinite. R equal to infinite when the circuit is open. When you don't connect anything, that means electron cannot move from one to other side. So that means the resistance is infinite. No, zero movement of electrons. That is infinite resistance. Now when there is infinite resistance, we have very high amount of voltage. Why? Because if you don't connect this n to p, then these electrons cannot move. Now this electron is moving because we have connected. Imagine if we don't connect. If we don't connect, then this electron won't move and they will accumulate. Electrons will accumulate here in n type, holes will accumulate here in p type, and there will be large number of potential difference. If we measure that potential difference, that is your VOC, voltage in open circuit, when electrons is not moving from this outside circuit. They are stored, they are accumulated. Now this acts as a cell, battery, because you are storing charges. Now once light, daytime, you are placing this solar cell in the daylight, sunlight, electron and hole pairs are created, they are stored. At night you can use it, you can connect this circuit, you can connect your light bulb here, and these electrons, because here these electrons, whatever electrons are here in n type, they will repel and they will come out from this direction towards this. Once electron moves in this direction, there will be turning on of light bulb, there is current. So here we get current when electron moves. Now what is short circuit current? that means zero resistance. Whatever electrons coming here because of this electron hole pair generation, they're then and they're moving. There is no storage. So no storage means no potential difference. That means in this I axis, in this vertical axis, there is no voltage, there is no storage of charge. That's why no voltage, but then current is very high. Why current is very high? Because resistance is zero, electrons are moving like anything, they are moving very fast. That's why you have very high current, but there is no storage, no potential difference. That's why V is zero. Now in between this, what is this region then? That means resistance is not infinite, not zero. Somewhere in between you have this kind of curve. So now from this curve, if you have understood why we have open circuit voltage high, because all the charge generated by light is stored and there is no flow of electricity, there is no flow of electrons. So the voltage is high, the potential difference is high here. No current. In this horizontal axis, no current. In this vertical axis, no voltage. In this horizontal axis, that means every electron and hole pair generated is stored and you have this much of voltage. Now you apply some kind of resistance, you provide some kind of resistance. Now resistance is not infinite, you are making it less, more and more less, further and further current will increase. And ultimately when resistance is zero, every stored charge will travel and will give you maximum current, but there will be no more voltage. Now from here researchers take a note who want to do research. That means that can we increase this voltage infinitely, indefinitely? If we continuously provide light, will this voltage increase? This light is creating electron hole pair. Now electron hole pair are accumulating in these regions. Here in this n side electrons are accumulating and this p side holes are accumulating. If you continuously provide light, will there be so many electron hole pair that this V, that this potential difference will become infinite? No, because if you create more and more electron hole pair by providing more and more light, at one time there will be so many electrons accumulated, they won't take in any other electron within them, they will repel them. They will say, okay, enough, there is enough space for electron, we cannot take any more electron. Now they will repel, because like charges repel each other. Same happens with holes in p side, because we have so many holes here. Now holes cannot, whatever electron and hole pair generated, that hole cannot come to this p side anymore. So in that way we cannot increase the potential difference, we cannot increase the voltage indefinitely. Now so what are the researchers trying to do? They try to increase the efficiency of the solar cell. So whatever light we are providing, for that amount of light we should have more voltage difference. So that is one target. And second target is we should get rid of all kind of impurities in the system. See, electron and hole pair should be generated only because of light, and they should not get recombined, they should be created in the depletion region. So all these criteria need to be satisfied, because in p side and n side, if they create it, instead of in depletion region, they will get recombined. So those are some of the criteria researchers are struggling with, so that we have efficient solar cell. Now it should be mechanically stable. If it breaks easily, can we use it? No. So it should be cheaper and widely available. This is actually major problem. The installation of solar panel is costly, and also it's not very widely available, it's expensive only. So those things researchers are struggling with. So another important thing, this is a recent work actually, uh, not very recent, I mean last 5 to 7 years, this work is going on, that not only storage where photovoltaic converts solar radiation into electricity, whatever I discussed, this was a photovoltaic mode, okay, where we store electrons and hole pairs and then use it for our purpose to generate electricity. Now instead of this, suppose say we don't have enough sunlight in some places, okay, some places are like they don't get sunshine for 6 months of the year. So what to do there? So in that case what we can do, we not only store charges but also store heat, so that whenever there is absence of sunlight, we can use that heat from the solar source only, from the sun only, will store the electricity and also heat to later on generate electron and hole pair when needed. So this is called concentrated solar power technology, where we not only store charges but also store heat of the solar source or the sunlight, so that we can use it later when we don't have sunlight. So this is the conclusion. Thinking of my days when I was in BSc Physics, studying in Gwalpara College, Assam. So I like this kind of lectures, but then more often it was like very hard to talk with them. I would have liked to know what they studied, uh, what inspires them. So I have just made suggest few books I have suggested which I liked reading so much. And since you are students of science, so these books you can study. Surely you are joking, but Mr. Feynman, this is like you'll enjoy. Okay, this is not very tedious, but then you'll enjoy the science here. For the Love of Physics by Walter Lewin, you can find these lectures in YouTube also. Very inspiring. I aspired to become a teacher like that, Walter Lewin. And that is huge aspiration. Now, Sapiens by Yuval Noah Harari. So these books you can try. I don't know how many of you have already read or what. And for soft copies, okay, you can, if you don't want to buy, you can go here, libgen.ly. You can get many books there. You can download. Um, and then obviously, since you are students of BSc Physics, you should think about your career options, your career choices. There are many job options in research labs to become scientists after BSc also. So stay updated. There are various platforms in Telegram, in you can subscribe in mail also, researcher job. See, I'm not advertising any of this actually I'm using, I'm customer of them. They are not charging anything, but I'm just sharing. Maybe it might help in any case. So researcher's job, faculty.com, that is for faculty. You don't need to go there. Researcher job and other platforms, you search, where you get continuous updates of what are the jobs available. Then you can try, you can see. If you don't know what is available, how can you move? And at least you should know what are the choices available to you. So okay, these are the references. Acknowledgement. I thank my colleagues here. They are very cooperative, because managing time here in this busy schedule, they help me a lot. And then I thank Ms. Rebecca Thapa for the initiation, and I thank HOD of Physics Department, St. John College, Dimapur. And thank you, sir, for the opportunity. Thank you.